So, welcome to the third lecture of module 2, that is on scheduling algorithms. So, in the last class what we have discussed, in the last class we have seen that there are several algorithms possible for the scheduling problem. So, in the last lecture, that is one lecture before the previous one. So, we have discussed the scheduling, allocation and binding problem. So, in that one we discussed that the first step in high level synthesis is actually the scheduling process, in which case for each of the operations we assign a control step. So, there can be several constraint driven synthesis, constraint driven scheduling, like we can say that we can have a time step driven constraint, like that is you have to complete all the scheduling in 4 or 5 time steps. So, then you have also discussed that there can be some kind of resource driven constraint, like you can have 2 multipliers, 3 adders, 4 subtractor kind of a thing, and also there can be resource and time constraint both, or there can be unconstrained schedules also. So, there we have defined different type of scheduling problem, and then we said that the focus of the main focus of this course is developing tools or algorithms which will automatically solve the problem for us. Then in the last lecture we have seen some of the algorithms like as soon as possible, as late as possible, then force directed scheduling. We have discussed these algorithms which can automatically given some constraints, like they are all time constraint based schedules. So, if you give a certain time constraint, then if you as soon as possible, as late as possible, or in the other case the force directed scheduling. So, these are some automated tools or automated algorithms you can say, which will given a time constraint and operations to be scheduled and a time limit, say 4 steps or 5 steps or k number of steps. So, these algorithms will tell you that within this time step, if I want to schedule your stuff or schedule your operation, then what are the minimum number of resources required. So, it will try to minimize the number of resources subject to the constraint of time as well as subject to the constraint of data dependency, that is very obvious. So, one thing I should mention that even if I do not mention this, that constraint A, constraint B. So, one constraint I may not say, but you have to remember that it is always there, that is actually data dependency constraint, that is one operation has to be done after that. So, nowhere whatever you do, you cannot schedule both the operations together, that is very important. Or if you say that operation I depends on operation j, so always operation j has to be scheduled after I. So, you cannot schedule j with I or before I. So, that is actually data dependency constraint, and even if I do not mention, you assume that this constraint is always there. So, based on time constraints, so you have to schedule the resources using the algorithms like as soon as possible, as late as possible, or force directed scheduling. They will give some steps to the of the operations, so that the overall resource requirement is minimized. Then we have said that as soon as possible, as late as possible, or FDS, force directed scheduling, are all heuristic algorithms. That is, they take much less time than the exponential overhead of time complexity overhead. They are time limits, time constraints, or time required to solve the problem. The time complexity is much lower, but they will always not give a very optimal solution. Their solution will be near optimal. So, for some cases we have seen in the last lecture that first as soon as possible gives a good result compared to as late as possible. For some cases as late as possible will give a better result than as soon as possible. Then we have seen that force directed scheduling is nothing but is a hybrid of these two algorithms. It takes advantages of both those and it gives a better result, what you call a better result in most of the cases compared to these individual algorithms taken by one at a time. But in today's class we will see some more algorithms, we will see one exact, and then we also say that there is some algorithms for exact algorithms, that is they will always give the optimal solution, but their complexity will be extremely high, that is exponential or even more than an exponential amount of complexity will be there. So, today we will discuss one such algorithm, that is the integer linear programming based algorithm. So, which will actually always give a very optimal or the optimal solution, the best possible solution in case of scheduling, and then we will show that it is a very difficult problem to solve, because we know that 0, 1 integer linear programming is an NP complete problem. So, these are very difficult or they take a long time to solve. So, that is why we go to the heuristics, which we already discussed in the last lecture. And then also we will show you some examples, like in the last example we have found out that force directed scheduling is a very good algorithm. It is giving very optimal results, where as soon as possible and as late as possible we are not giving. But in the end of today's lecture we will also see some cases where force directed scheduling is also not giving a very optimal solution, as they are giving near optimal solution. So, in that case, that integer linear programming is a very complex problem. Complex, it takes long time, or it gives time to take, or it is high, it is a very high time complexity to solve the problem, but still it gives the most optimal solution in all cases. So, this is in nutshell what we are going to learn today. Okay. So, let us start. So, one more. So, now in the last, as mentioned in the last class, we have learned about FDS, as soon as possible and late as possible. They were all time constraint based solution. Now, in this, now we are going to see there is some kind of schedulings which can, some kind of scheduling algorithms which can solve the problem for what you call the resource constraint. So, one is actually called the least scheduling. The first one is the least scheduling. So, as the name says, so what it says. So, as the name list scheduling means we have a list. So, we have a bin. So, we have a list or a bin. So, it says in a bin there is, it says that we have so many number of multipliers, we have so many number of adders, we have so many number of what do you say, another adder called dividers, so forth. So, different different resources will be there in a bin, and there is a list which is actually called the ready list. So, what do you mean by a ready list? Ready list means these are the operations which can be scheduled right now. That how can you say that the operations can be scheduled right now? That is, all the data on which they are dependent on have already been scheduled. Like if operation is dependent only on inputs, then you can schedule in the first step, and if an operation is dependent on data I and data j, operation I and operation j, so operation I and operation j has to be scheduled before the operation we are talking about has to be scheduled. So, based on this data dependency constraint, you can find out that these are the operations which can be scheduled right now. So, that actually comprises the ready list, and we have a bin of hardware. So, you have to find out that we have to try to schedule all the ready operations in now, if you can do that using your bin. That is, we say we require 3 multiplication operations to be scheduled now, because they are now ready to be scheduled, but you have only 2 multipliers in the bin. So, if you have 2 multipliers in the bin, then you have to use 2, and one operation will be left which have to be scheduled in the next time step. Now, which one of them, that will be, you can use some priority function and all, that we will see. So, that is basically the idea of list scheduling. In list scheduling, actually we basic idea is that we have a maximum number, we try to schedule maximum number of operations in the control state subject to resource constraint and data dependency. Okay, so here data dependency is automatically taken care in the what do you call these the list. When you are preparing the list, so we prepare the list based on data dependency, but there is actually a bin which stores the maximum number of operations. So, based on that you have to try to schedule as many operations as possible in a time go. Okay. So, as there is a list, so the name ready list, because we are taking a ready list into account, so the name list scheduling. Okay. So, now how long you have to go? As long as there are operations in the ready list, we have to go about increasing the time step one by one, and you have to keep on scheduling the stuff. So, you can understand that this is not a time constraint based schedule, it is a resource constraint based schedule, because here we have a bin of resources and you have to keep on scheduling the operations until you have scheduled all the operations and subject to whatever hardware you have in your bin. So, that means you may take a very long number of time steps also, that is also possible in this case, because we are not having any, we are not thinking about the time constraint, we are only thinking about the resource constraint, and we are saying that keep on scheduling all the elements from the ready list as much as possible subject to the availability in the bin, and you have to keep on doing it as long as all the operations are scheduled. So, you have to keep on increasing the time step. So, this is basically a ready, this is basically a resource constraint based schedule. So, it also says that if there are more than one operation which can be scheduled in one time, but you cannot do that because of resource constraint, then any one of them has to be scheduled. So, that you can find out based on some priority function. So, what can be, there can be lot of priority functions. So, what are the very common types of priority function? So, one very common type of priority function you can say is the range in as soon as possible and as late as possible. Okay, so, you can say that, say for example, this is time step. So, one operation can be scheduled here, one operation can be scheduled here, one operation can be scheduled here. So, this range is 3. So, it can be scheduled any one of them, but there can be say one operation, so which has to be scheduled only here, that is this I can say this. So, this can be scheduled anywhere. So, you can do this, but there is one operation, say this is say 1, 2, 3 and 4 operations, it can be scheduled only in this side. So, there is no other choice for this. Okay. Sorry, this is O1, this is also O1, and this is also O1, and this is O2 basically, sorry. So, O1 can be scheduled in the 3 time steps 1, 2, 3, but O2 can be scheduled only in time step 1. So, by as soon as possible and as late as possible, by as soon as possible you will schedule O1 at step 1 and O1 at, and as late as possible you will schedule O1 at 3. But in this case for O2 you have to schedule O2 in time step 1 in both as soon as possible and as late as possible, because there is no other option available. So, now if you have say both of them are say adders. Now, you say in a bin you have only one adder. So, bin you are having only one adder. So, now what you will do? So, you can schedule either 1 or either 2, because both of them say are dependent only on the primary input. So, both of them can be scheduled. So, in the ready list you will have both 1 and 2. So, now which one you will schedule? You can schedule any one of them. So, that is actually your priority function comes into play. Now, you find out that you have only one bin. Okay, so, and say there is some other operations over here that also to mention, there is O3, O4 something like that. So, it is the range is not that much flexible here. So, there are a lot of other dependencies for O2. So, it is in as soon as possible and as late as possible its position is only becoming at 2, okay, because of some other stuff over here. So, now you have the question that whether I will schedule 1 or whether I will schedule it 2. You can schedule any one of them, because both of them are ready. Now, the priority function is that if you have some range in as soon as possible, as late as possible, that range, if you find that O1 can be scheduled schedule between these, there is no problem. Then but in O2, because of some data dependency, it has to be scheduled over here by this range, then you better schedule O2 here and go about it. The motivation behind this is because O1 has lot of flexibility, so you can refer it to any other place, but O1 is actually hard coded over here, or its range is very less compared to O1. So, you better schedule it, I mean give priority of scheduling this one over schedule O2. So, you give preference to schedule O2 then compared to O1 scheduling at time step 1. So, this is one kind of a priority schedule. So, one kind of a priority function. So, there are I mean so operation with small ranges are given priority because I mean there are the less number of I mean if the operation has less flexibility, then it is very less probable that you can be able to force O2 to this step or this step, or even if you want to do that, so your time schedule will be increased. Like if you schedule, if you drop this one here, then all the other operations will be again shifted down. So, there is a possibility that what may happen is that, so whole time length may increase. So, basically what they are saying that a priority function is what? A priority function is if there is a conflict, a conflict, if there is multiple choice you are having, that now you can schedule operation 1 or operation 2, but only you can schedule any one of them because of the resource constraint, then you take the one which has a which has a low flexibility, because low flexibility means there is a very high probability that it has to be scheduled in the time step now to have a overall optimal result. But if there is a long of flexibility here, so you can wait till the next step. So, this is one kind of a priority function. There can be many other priority functions, like sometimes we think that dependency, say one operation, it controls n number of other operations, like operation I. So, it is actually operation, say some operation I, now operation j, k, l, m, x, y, z all are dependent on I. So, you better schedule operation I compared to operation m, on which nobody is dependent, or only one or two operations are dependent. So, if you find that there is one operation on which many other operations are dependent, so you better schedule it now or give priority to that compared to any other which is having less number of operations which are dependent on it. So, there can be lot of priority functions you can generate, and as I already told you, they are all heuristic based functions. So, what you can do, you can find out different types of optimal functions or priority functions, and then you can find out which is giving the best actually. In this case, you are having a resource constraint and you are trying to minimize the number of time steps. So, you just find out that based on the resource constraint, which priority function is giving you a better solution in terms of number of time steps. So, there you can find out different type of priority functions based on your requirement. So, as I told you, they are all heuristics. So, it is not guaranteed that you will get an optimal solution, but it is highly possible that you are going to get a solution which is near optimal. Okay, now let us see the scheduling algorithm in a formal terms, and then we will go about for an example. Okay, so what is this scheduling? It says the operations you have to take and maximum number of operators of each type. So, as I told you, this is actually what? This is actually a resource constraint based schedule. So, if it is a resource constraint based schedule, then what is happening? So, we are not giving any constraint on time, rather we are saying that k max, that is of, I mean if the k max for each type of operation like adder, multiplier, subtractor, divider, etc., we define a maximum number for each one of them. We can say that 2 multipliers, 1 divider, 2 subtractor, 1 adder kind of a thing, and then you have to control step for all the operations. If this schedule is successful, else you have to report a failure. Now, what is this? So, what you have to do? First, you have to prepare ready list 1. So, what is ready list 1? Ready list 1 means all the variables which can be scheduled in time step 1. Now, which operations can be scheduled in time step 1 if you think? So, all operations whose predecessors are input variables, like you have some operation like whose depend on only on the primary input. So, all operations whose depend on the primary inputs can be scheduled right now. So, they comprise ready list 1. Now, what you do? You take each operation from ready list 1 and try to schedule all elements of ready list in one control step 1 if there is no violation in resource constraint. If there is a violation in resource constraint, then you have to schedule any one of them using a priority function. But if there is no resource constraint, then based on this k max values, then what you can do? You can schedule all the operations in ready list 1 and that is done. But if there is, you find out that only one of them or two of them can be scheduled, then which two of the n can be scheduled right now, then you have to set in a priority function. That is what thing you have to do in the first list. Based on the first list you have scheduled, whatever is based on the requirements or based on your constraint on the bin, that is maximum number of hardware available, you schedule some of the operations in time step 1. Then what you do? Then you have to repeat this till all the operations in the time step 1 is scheduled. That is obvious. Now what you do? Now you go for preparation of ready list number 2. You have to prepare ready list as long as all the operations are not scheduled. So what you will do in ready list 2? In ready list 2, what you will have? All the operations which were dependent on the variables or all the operations which have now been scheduled in time step 1. So now they will be getting enabled. So there can be some operations which were dependent on the operations which are now scheduled in time step 1. So now you can schedule those elements which were dependent on the operations scheduled scheduled in time step 1. So, now they get ready. Also, some of the operations which you could not schedule in time step 1 because of the resource constraints will also get in the ready list for the time step 2. Now, you have to repeat this based on the subject to constraints of the hardware available, you schedule whatever is available in the resource step 2. So, whatever ready available in the ready list 2, you schedule them. Some of them again will not be able to be scheduled because of the resource constraint, then you have to bring it to the third list, and also in the third list those elements will come in picture which were dependent on the data dependent on the elements which are now scheduled in time step 2. So, you have to keep on doing it for all lists, you have to keep on doing it till list j such that all the operations has been scheduled. So, in a general way it is saying prepare ready list I for the next control step, schedule all operations in this in control step j if there is no violation in request constraint, and you keep on doing it, you have to repeat this till all the operations have been scheduled. That is what is the idea. So, it is very simple. So, you actually prepare ready list 1, schedule as many as possible based on resource constraint, whatever is remaining you make it in resource list 2 as well as you whatever else you have to put in resource list 2, all the operations which were data dependent on the operations which are now scheduled in time step 1 will get into time step 2, and you have to keep on repeating it as long as you have scheduled all the operations. So, let us take our old example, that is this one, this is what we are talking about, and this is our running example in the last 2 lectures. So, we will try to schedule them. Already we have scheduled this operation out 1 and out 2 operations in FDS as soon as possible, as late as possible. Now, we will try to do it in using list scheduling. So, now according in the previous case we had given a time constraint of 4 and we are trying to do that, but now here you cannot give any time constraint because it is a resource constraint schedule. So, you have to give a resource constraint. So, in this case we are saying that 1 max, 1 is type multiplier, we have 2 multiplier, 2 is divider, we have 1 divider, 1 subtractor, type 3 is subtractor, and 1 adder, that is 4 is 1. Okay, and this is the thing. So, let us try to try to go for a list schedule when this. So, what you remember that we have 2 multipliers, 1 divider, 1 subtractor, and 1 adder. Okay. So, this is actually just the as soon as possible schedule for this, just I am giving it as a view so that you can recall. So, you can remember that O1, O2, O6 and O8 can be scheduled in time step 1 because they are dependent only on the primary input. So, this one will actually belong to your ready list 1. Okay. Now, if you can schedule all of them now in the first time step, then this one will become your ready list 2. But for some reason say you cannot schedule operation 6 in time step 1, then actually this guy will become to ready list number 2, and the ready list number of 2 will comprise all, it will not comprise this because its dependency is remaining, it will comprise this because now all this has been scheduled, it will also comprise this because this has been scheduled, and this guy will join from the ready list 1 to ready list 2. Because of some time constraint it was not able to schedule, because of some resource constraint O6 was not been able to be scheduled in time step 1, so it will join time step 2 and so on. So, you have to keep on doing it over everything is scheduled or not. Okay, so, this is just in a nutshell. I mean, we will go for the elaborate explanation of the example, but for the time being remember that O1, O2, O6 and O8 can be possible to be scheduled in time step 1 or in the ready list 1 because they are only dependent on primary inputs. Now, let us see. So, in step 1 ready list 1 comprises O1, O2, O6 and O8. Okay, all this can be scheduled. Now, we cannot schedule all the multiplication operations because 1 max is 2. So, O1, O2, O6 only 2 of them can be scheduled. Now, which 2 you have to schedule? So, again let us go back to our priority function. So, you can see this, that if you are going for as soon as possible and as late as possible stuff, you can see that if you remember the last lecture, these 2 multipliers are fixed, their range are very less. So, there is very less mobility, but this guy and this guy they can be scheduled here also. Okay, this is the divider and this is the star. So, this guy is having a mobility of 2. That means you can schedule it here or you can schedule it here, that is possible, but these things get freezed over here. Now, if you try to push these guys down, so time step will definitely start increasing. Okay, so, according to priority we should schedule O1 and O2 and defer O6 because O6 can be scheduled because this is the flexibility, so you can push it over here, correct. So, this is the case. Okay, but now say it would have been the case, just assume that O6 was also not flexible, then what are you going to do? Then you have to take any 2 of them and do the scheduling. Say for example, we may have deferred this guy. So, if you have deferred this guy, what is going to happen is that, so this guy will come here, then all this thing will come one step down. So, you will have addition increase in the number of time steps. So, better we go for the priority function we take. So, in this case there is flexibility in O6, so we will defer O6 over here. So, that is what is being said. So, the mobility is shown in this figure. So, we have discussed. So, O1 and O2 is 0 while this one mobility is 2. So, we schedule O1 and O2 in time step 1, okay, and we will see later what we can do about it. So, one O1, O2 is scheduled over here and O6 we defer. So, in ready list 2 what will come? In ready list 2 you will get O3 because its predecessors are scheduled. Okay, now O7 will not come in ready list 2 because this guy is not yet scheduled, but O8 can be scheduled in time step 1 because we have already one multiplier, also one subtractor, because resources is one multiplier, 2 multiplier, if you remember 2 multiplier, 1 divider, 1 subtractor and 1 adder. So, you require one subtractor over here, so you can easily schedule this in the first time step, that is not a problem. So, now in the next time step on list 2 you will have O3 because its predecessors are scheduled, O9 will be there because its predecessor is scheduled, and O7 will not be able to be scheduled here because its predecessor is not yet scheduled, but this guy will join in the ready list 2. So, in ready list 2 you will have O3, O6 and O9. Now, here you can schedule all of them because we require one divider, one multiplier and one adder. So, you can easily schedule them. Okay. And similarly, we can go about doing it. So, let us look at this example in a pictorial manner. So, what is in ready list 2? Ready list 2 we have O1, O2, O6, O8. So, here mobility is 2, here mobility is 3, here mobility is 0. So, mobility is 0 means you cannot move these guys from here and here compared to as soon as possible and as late as possible. Here the mobility is 3 because you can put it here, you can put it here. So, 1, 2, 3. So, this guy can be here and here. So, this guy is 1, 2, 3, 1, 2, 3 kind of a thing. Correct. So, now, you are writing mobility 3, mobility 2, mobility 0 and mobility 0. So, now if you remember already, so we have only 2 multipliers. So, we better schedule these 2 because the mobility is 0, we defer it, okay, and this one subtractor, so you schedule this. So, in time step 1 we have scheduled all the 3 operations excepting this one. So, now in the ready list this guy is going to join, okay, and O3 will come because its predecessor O1 and O2 has been scheduled. So, it is coming over here, and O9 is also here in the ready list 2 because its predecessor O8 is scheduled. So, now you have here. So, here we require one divider, one multiplier and one adder. So, it is satisfying your time resource constraint. So, you can schedule these 3 guys over here and it is your schedule list 2. Now, what happens? So, now what do you get in ready list 4? So, in ready list 4 if you remember here, if you see over here, so till now we have scheduled up to this, already has been scheduled. So, in ready list 4 this one can be scheduled because its predecessor temp 3 and A has been scheduled. A is primary input and its temp has already been scheduled. Okay. So, that will actually come over in time step 4. So, you can see there are 2 operations and this one is there, and also this guy has been scheduled here. Okay, so, if you see that we could not schedule O6 over here. So, now we have scheduled O6 over here, has been scheduled O6 has been scheduled over here, this guy has been scheduled over here. So, in time step 3, that is in ready list 3, we have this guy because his predecessor temp 3 is scheduled as well as A is the primary input, and for O7 this predecessor is O6. So, that has also been scheduled in time step 2. So, in list 3 we have O4 and O7. So, actually this is what is being shown over here. So, in this case we have O4 whose predecessor is we have this is the ready list 3. So, O4 whose predecessor was O3. So, its result is done, and A is also, it is on O4, this is O3 and it depends on A. So, this guy can be scheduled over here, and O7 is dependent on O6. So, O6 actually controls the O7. So, O7 now O6 is already scheduled in time steps 2. So, O7 can be scheduled over, it comes in the ready list. So, in other words, the predecessor of O4 and the predecessor of O7 has already been scheduled in time step 2. So, these 2 guys will come in ready list 3. Now, we have it requires one subtractor and one divider, we have that. So, both of them will be scheduled in time step 3. So, now we have completed up to this much, this one up to this all the operations have been scheduled. These 2 guys have been scheduled here and here. So, they are not scheduled over here, that is these 2 O6 and O7 are now here and here. So, this is what has been the case, and now only one thing is remaining, that is what you call O5. So, now it can be in the ready list number 4 because it is dependent on O7, which is now been scheduled in O3, that is time step 3. So, O5 which is dependent on O7 is now already scheduled in time step 3, as well as it is also dependent on temp 4, which is the output of O4, and O4 and O7 have been scheduled in O4 and O7 which are actually controlling O5, they have been scheduled in time step 3. So, they will O5 will actually be now in ready list number 4. So, in other words, the predecessor of O5, that is O4 and O7 has been scheduled in time step 3. So, O5 will be joining ready list 4. Now, you can see that ready list 4, that is actually O5, it is dependent on O7 and O4, which has already been scheduled in time step 3. So, this will be coming in ready list, O5 will be coming in ready list 4, and you can see that it requires one subtractor to be implemented. So, this guy will be scheduled over here, and finally what do you get? You get a schedule in which case in first step you schedule O1, O2 and O3, in second step you schedule O3, O6, O9, okay, and in the third step you schedule O3 and O7, and finally you schedule O5 and O4 kind of a thing. So, this is a list schedule. So, you require 4 time steps and your schedule is done basically. So, here actually you see that I mean in this case we have got a time step 4 because our constraint was 2 multipliers, 1 adder, 1 divider and 1 subtractor kind of a thing, but you can also try, like if you can make this as 1, then you can find out that you will require much more number of time steps to solve the problem. Okay, so, this constraint was very similar, this resource constraint was very much similar to what was required, you have found out that in case of FDS. So, if you think that in FDS we started with 4 time steps and finally we said that we require this many number of stuff, okay, and now in case of list we actually started with this resource overhead and we found out that we require 4 time steps. Okay, so, indirectly I mean we started with, in one case we started with a resource constraint and we landed into a time, and in the other case we started with a time constraint and we landed into a number of resources. So, we saw that both of them are equivalent. I mean this is not a very important thing to be noted, but the idea here is that I mean with this many number of resources you can solve in 4 amounts of time, and in 4 amount of time or 4 time steps you can solve using this many amount of resources. That is what is the idea, but you can try at home or you can try yourself by making the multiplier equal to number 1, then you can find that the number of steps required will be much more higher. Okay, so, this is one heuristic, in which case our constraint is basically nothing but it is based on resources. So, we have a set of resources and in each time step we try to schedule as many stuff as possible based on the availability of resources, and if you find out that this is not there, then you have to defer it. And how do you defer, which one you defer, it is based on some priority function. In this case our priority function was range. You can take any other priority function like how many operations it is controlling and so forth. Okay. So, till now whatever algorithm we discussed, like as soon as possible, as late as possible, force directed, and then this one is what, this one is rescheduling, they are all heuristics based schedules. Okay. Now, we will see an exact algorithm which is actually called integer linear programming based scheduling, in which case you are always guaranteed to get the best possible solution. In this case, for some example we will get a good solution and some example we will not get an optimal solution. Therefore, in the question answer session today we will see one example in which case FDS will not give you an optimal solution. But in case of ILP, always you are going to get a optimized solution, that is a guarantee. But now what is the problem? So, in this we know that integer linear programming is a NP complete problem. So, this time complexity will be exponential, the number of time steps, number of operations and so forth. So, you can assume that if I have 100 time steps, so the complexity will be 2 to the power 100, and if I have around 500 operations, the complexity will be around 2 to the power 500 plus. So, it is a very difficult problem to be solved using a feasible time in a computer. So, that is why we always go for whatever heuristics we have learned. But again, as I told you, you have to formally know that the scheduling problem is a very difficult problem to solve. So, what we do is that in this case, we try to map the scheduling problem to a well known problem which is NP complete, NP hard kind of a stuff. So, in this case what we will do, we try to show that our scheduling problem can be mapped to 0-1 integer linear program which is known that it cannot be solved in polynomial time, which proves that there cannot be any polynomial time solution to integer linear program. I mean cannot be any as there is no known polynomial time solution to 0-1 ILP. So, you cannot develop a very good or you cannot develop a polynomial time solution for the scheduling problem. So, therefore, you have to save time and you have to give a reasonably good answer, you have to go for heuristics. So, all the algorithms we learned till now are heuristics, and still people can develop better and better heuristics which can serve you better. So, what is the job of the heuristic? The heuristic's job is to run in a reasonable amount of time, and you have to give a solution which is as close to the optimal as possible. So, that is what is the chase about. So, we always try to find out better and better priority functions. You can find better and better heuristic algorithms which will take less and less time to run and yet or a reasonable amount of time to run and yet give you a solution which is very close to the optimal solution. And it should not be like that your heuristic is working better for one class of algorithms, it is not working bad, it is not working good for another class of circuits. It should not be the case. That is, I mean, you should try to develop a heuristic which covers a reasonably wide range of circuits. It should run in a reasonable amount of time and it should give a solution which is very close to the optimal. That is the basic goal of developing a heuristic algorithm. Okay. So, let us come to our integer linear programming based stuff. So, in this case ILP is actually well known to be solved is used to be solved for a very wide range of problems which are based on optimization constraint based optimization. It is not only related to VLSI, it can be related to production, it is related to biotechnology, it can be related to engineering, physics, and any science domain of engineering or whatever, wherever you want, or business even, or finance, economics, where you have some resources and some constraints, or wherever you have some constraints and you have to satisfy the constraints and you have to reach to some optimal value. There you can use integer linear programming to solve this stuff. So, we will see how integer linear programming for optimally solving the synthesis problem and high level synthesis problem, basically the scheduling step. Okay. So, the biggest advantage of ILP is the quality of solution. So, unlike heuristics, you are always bound to get the best possible solution. Okay. But the time taken is not polynomial, because I told you ILP is known to be, there is no known well known, or there is known that till now means the NP complete time of problem. So, now till now you do not know whether there exists a polynomial time problem solution to ILP or any of these NP type of problems. So, that therefore, we know that there is no well known, or it is very difficult or almost impossible if you think still an open problem in computer science whether P is equal to NP or P is not equal to NP kind of a thing, but as of now still nobody knows a polynomial time algorithm to the NP complete problems. So, you can think that it is almost impossible as we stand now to develop a easy or a less complex solution or less complex time solution for the 0-1 ILP and hence for the scheduling problem. So, there is actually a trade off how fast you want to get the solution and how close you want to go to optimality. Okay. So, now we will formulate the whole problem, whole integer linear, what you call this our scheduling problem into integer linear program. But unlike our previous discussion where we have given a general algorithm, in this case we are not going to give you a general algorithm, but let us will take an example and then we will try to see how a problem, how a scheduling problem can be mapped to 0-1 ILP. We are not going for a general algorithm because there are very well known tools which will actually solve these ILPs, and no one actually uses integer linear programming to solve the scheduling problem because of the complexity. So, telling you was very general and a complex mathematical algorithm is not at all our purpose in this course, because we just want to focus so that you learn how you can map a general problem to a NP complete problem or a NP polynomial type problem. So, if say for example you are given problem X, now you are asked how can you solve the problem, or can I develop a polynomial time algorithm for this, or is it not possible to develop a polynomial time problem for this? How do people solve the problem? It is not like you can say that I have tried for 100 days and I could not find a polynomial time algorithm, so there is no polynomial time algorithm for this. Nobody will take your argument. So, how do you do that? So, you have to show that I have proved formally that this problem is equivalent to a very well known integer linear programming kind of a stuff, or it is very well known to one of the well known NP complete problems, and as there is no well known polynomial time solution to this, so you know that there will not be any polynomial time solution for my problem also. So, what we do? We try to map our problem to a very well known we try to map our problem to a very well known what you call a NP complete problem, well known NP complete problem, and then we can prove it. So, but it is not good, or what do we say, that it is not very idealistic in this course to tell you a formal algorithm how to do that, because this is a course which is taught in formal systems or foundation of computer science. So, better what we do is that we will just show how we can map our scheduling problem to 0-1 ILP and then prove that this is a very difficult problem to solve, or it takes a long time to solve it. So, what do we do in ILP? So, we have to capture some constraints and we have to find and you have to optimize some stuff. Okay, so, let us see. So, what we do? So, we will try to optimize the resources, that is what is the thing. So, let us take the resource constraint based ILP, also you can formulate for time constraint based ILP, that also can be done. Okay, so, let us see how it will do. So, what we will do? We will capture the range in which the operation can be scheduled, that is the first thing. So, we will say that our time, we are giving some kind of a time like this, then actually we are trying to find out what is the flexibility of the operation. So, in what range you can schedule your operation. Next, we see that there is no resource of any no violation of any resource constraint, that is our resources are constrained, and obviously data dependency, as I told you, data dependency is mandatory to be satisfied. So, you have to say that if resource I or operation I is dependent on operation j, so operation I is dependent on operation j, so j has to be scheduled before I. So, that data dependency has to be matched, and then you optimize the in this case you can say that there is no violation of resource constraint. So, you can optimize this resource constraint. So, what do these two statements say? So, actually you have to say that I have 10 adders, 10 multipliers, 10 subtractor kind of a thing. So, you should not violate this, and then what do you optimize? So, you take as less resource constraint as possible. So, that is the idea. So, let me just tell you in some around another way of stating it. So, what do you say, give as an equation, or how do you formulate the problem? So, we first say that we have to represent that what is the mobility of these operations. Like we first given a time, we generally take a time constraint kind, say, I mean, we are actually formulating the time constraint based stuff. So, we say that these are 4 times step or 5 times step, whatever is required, that you first draw. So, that is your time constraint. Whatever you have to do, you have to, initially I told you that it is actually resource constraint based, constraint based scheduling, actually is not that. So, what we will be learning in this case is it is a time constraint scheduling. Our scheduling will be time constraint, and what will be optimized will be the resources. Okay. So, initially, sorry for that what I have told you. So, in this ILP, our time will be fixed, that is your time is constrained. So, it is time constraint schedule, and what you are going to optimize? You are going to optimize the resources, you are going to take as minimum resources as possible, that is like our SF, as soon as possible, as late as possible, or in the other words or FDS kind of a thing. So, first you fix up your time, and then you find out the range. So, what is the flexibility of this? So, those things you have to represent using integer linear programming equations, that we will see how you can do. Next, you see that you give some resource constraints. Okay. So, now what is a resource constraint kind of a thing? Say 5 multipliers, 10, 100, you can give a very high amount of resource also, that is not at all a problem. So, but there is actually because we are not, you can also say that our resources are very high, 10 adders, 10 multipliers, 10 subtractors, all those things you can give. These are lot of very tight constraint. You just give some kind of resource constraint using the equation, we will see that. And you have to obviously represent the data dependency, that if I is dependent on j, so one cannot be scheduled before the other kind of a thing. So, I is dependent on j, so I cannot be scheduled before j kind of a thing, that is your represent, and you will again optimize the resource constraint. So, what is this? So, here you are saying that I require 10 multipliers, 10 adders, 10 subtractors, some numbers you give, and then what you do, this automatically the ILP will actually take as minimum resources as possible given this time period. That is what we are going to do. So, this is some constraint you have to fix, because otherwise we may not land up into a, we will not be able to formulate the ILP. So, you can also give a very high number of resources, that is not a problem. But automatically you will your ILP will optimize the number of resources that required to be taken. Okay, so that is the idea. So, if you can remember, in as soon as possible or as late as possible, we never thought about the resources. What we have done? We have taken the time to be 4 or 5, and then we have tried to use as minimum resources as possible. That is actually ILP, that is equal to as soon as possible, as late as possible, or FDS. So, given a time constraint, we are not putting any kind of resource constraint, but automatically the algorithm is trying to use as minimum resources as possible. So, that is what is being done. So, in this case also we were giving some resource constraint, that is we can put it in a bit relaxed manner also, and if you make this one very tight, then you can think that it will become resource time constraint based scheduling, it will come into picture. But actually we first generally, in case of only time based stuff, time based scheduling, where with time constraint scheduling we can just give a wide range of resources, and then we will try to see as minimum resources as taken. So, it will automatically optimize. So, what is the formalism we will be using? So, Oj, that means scheduling operation I in step j. Okay, so, this is actually the variable in ILP, and it is a 0 1 ILP. So, it can take the value only 0 and 1. Okay. So, for scheduling, first we have to specify the ranges in 0 1 ILP. So, how do you go about it? Okay, so, in this case, if you see our stuff, okay, sorry. Same algorithm we will be taking. So, you see this is the same algorithm we have taken. So, for this one we are already learning. So, this is the one. So, just remember that this is the same example we will be taking. So, first you have to represent some excuse me, some constraints using 0 1 ILP. So, first constraint is the range. Now, you can see that in this case, say we have taken 4 time constraint based schedule. So, you know that O1 cannot move, O2 cannot move, O3 cannot move, O4 cannot move, and O5 cannot move. That is the basic problem. This one can move 2, this one can move 3. So, that you have to represent by some equation. And what are the variables of the 0 1 ILP? Oj. That means what? Oi means ith operation in step j. So, if you write O11 equal to 1, then what it says? It says that variable O11 has to be a 1 in the ILP. If you write O21 equal to 1, that means it says that variable O21 has to be a 1 in the 0 1 ILP. What does it imply? It implies that O operation 1 has to be scheduled in time step 1, and that is actually 1. That means operation 1 must be scheduled only in time step 1 and nowhere else. Similarly, if you write O21 equal to 1, it says that operation O2 Operation O2 has to be scheduled in time step 1 and that is mandatory, because we say that O2 is equal to 1. But now let us just see for this one, then it will make your stuff clear. We write O61 plus O62 equal to 1. So, sorry, O62 equal to 1. So, what does it mean? It means that O61 can be scheduled over here, or O62 is equal to 1. That means O6 can be scheduled. If O6 is scheduled over 1, then this is equal to 1, and if O6 is scheduled in 2, then O62 will be equal to 1 and this will be equal to 0. So, this one is the case. So, if operation 6 is scheduled in time step 1, then O61 will be equal to 1 and O62 will be equal to 8, satisfying the equation. And the other way, if operation 6 is scheduled in time step 2, then what is going to happen is O61 will be equal to 0 and O61 has to be 1 to make it a 1. As I already told you, it is a 0 1 ILP. So, all the variables will have a value of 0 and 1. You cannot have values like 2, 3, 4 or 0.5 or 0.7, anything like that. So, what are the solution to this one? There is only two solutions, 1 0 or 0 1 for the variables. You cannot have 0 0 or you cannot have 1 1. So, what does it say? That either 6 will be scheduled in 1 and or 6 will be scheduled in 2 for the equation. For O8, what we can write? O81 plus O82 plus O83 is equal to 1. That means 8 can be scheduled in 1, then this one will be 1, other 2 will be 0. If O8 is scheduled in here, then this one will be equal to 1, this one will be equal to 0, or O8 if it is scheduled in time step 3, then this guy is 1 and these two are equal to 0. So, if you can write like this, then the first set of constraints, that is the range, capturing the range of the operation is actually done. Okay, so you can see we write O1 as 1, it implies that for the ILP O1 can be only have the solution 1, that is operation 1 can be only scheduled in time step 2. We write O61 plus O62 equal to 1, that means fact that O6 can be captured in time steps 2 and 3 and so forth. Okay, so in this case as I told you, either this one is the solution or this one is the solution and nothing else. So that means either 6 can be scheduled in 1 and 6 can be scheduled in 2. So this is our actually range. So for all these guys, you will, in this case you will have O51 equal to O5 4 equal to 1, in this case you will have O4 4 equal to 1, in this case O3 2 equal to 1, and in this case O11 equal to 1 and O21 equal to 1. In this case is 2 range, so O61 plus O62 will be equal to 1, in 7 it will be O72 plus O73 will be equal to 1, in this case will be 3 in ranges. So, these are basically your equations. So, it says that O1 is 1, O2 is 1, 3, 4, 5. So, this is the chain corresponding to this one which is already fixed. Now, these are for the operation of 6 and 7. So, you can move about these two guys to 2 steps. So, it says that 6 1 plus 6 2 is 1, 7 2 plus 7 3 is equal to 1, and this corresponds to, these two guys. So, this one can move between 1 2 and 3, this can move between 2 3 and 4. So, this can move in 2 3 and 4, this is what is being written. So, this equation actually captures the range of scheduling. Now, what is the next one? So, next one is the requirement, there is no violation of resource constraint. So, in this case, as I already told you that this equation and this ILP is actually based on, you will optimize your resources based on the time constraint based scheduling. So, you can give some resource constraints, you can put some, basically you can put some higher end also. So, in this case, well, again you have to say 1 max, 2 max, 3 max and 4 max. That is based on the 4 or n different types of operations you have. So, 1 can be your multiplier, 2 can be a divider, subtractor and adder. So, it is multiplier, divider, subtractor, adder. So, whatever type of operations you have, so those different types you will have, and you have to define some maximum. Okay. So, now what is the case? Now, you can now say, so these are some values. Okay. So, generally we write these values. So, these values we will see. I mean, this will be optimized later. So, we just write this as a symbolic values right now for the time being. Okay. We are not putting any kind of values, that is why I told you. I mean, we can think that there can be very large in number. So, otherwise I mean you may be getting confused by looking at this, that we have some requirement, there is no violation of resource constraint and we optimize the resource constraint. So, that is why we told you that writing this here means that you can write some values and you can think that they have a very high value, or you specify a very high value, 1000, 10,000 or something like that. Okay. For the time being, that is why we actually write them in a very symbolic manner, right? 1 max, 2 max, 3 max and 4 max, and then we will try to optimize this. Now, you see one thing. So, now what will be the case? How do you write the values? So, in this case you see, let us come back, let us go back to our old stuff. This one is our old stuff. So, you can see in time step 1 what you can schedule. In time step 1 you can schedule for the multipliers, okay, that is type 1 max. So, what you can schedule? You can schedule O11, O21 and O61. So, these are the multipliers which can be scheduled here. So, O11 plus O21 plus O61. So, So, that should be less than or equal to 1 max. That means what I am saying. So, O11 means, so one multiplier is scheduled over here. O21 means another multiplier is scheduled over here. O61 equal to 1 means another multiplier over is scheduled over here. So, if you schedule all the 3 multipliers in 1, so it will be 1, 1, 1 and then it will be 1 plus 1 plus 1. So, it will be 3 multipliers and that should be less than equal to 1 max, that is it should be less than the total number of max multipliers which you are having in your sum case. So, initially it can be very high and then you can think it is very high, you can think, I am again saying quote unquote think, this is a very high in number and then your optimizer or 01 ILP based optimizer will take as minimum as possible. Now, you can also think in another case, that is O8 also can be scheduled over here. So, you can say that O81 should be less than equal to, say in this case 3 is corresponds to subtraction. So, you can write that this is less than equal to 3 max. Now, let us go to time step 2. So, in time step 2 what is going to happen? So, there can only be one multiplier which can be scheduled over here, only this one can be scheduled over here, there is no other multiplier. So, in this case you can write it as O62 is less than equal to 1 max. Okay. Now, you consider about in time step 2 about the dividers. So, you can have 2 dividers over here. If obviously if 6 is scheduled over here, 7 will go down, but for the time being you know that there is a possibility if 6 is scheduled over here, 7 can be scheduled over here, there is a possibility. So, you write O32 plus O72, if you add this there are 2 dividers, so it will be less than equal to 2 max. Okay, because sorry O62, this is because the dividers. So, the number of dividers, if O32 is 1 then this one divider consumed, O72 equal to 1 then another divider consumed. So, 2 dividers if you schedule, so that should be less than equal to 2 max, that is 2 max is the maximum number of dividers which is available. Similarly, there is also one adder can be scheduled over here. So, you have to also write that O92 okay, should be less than equal to 4 max, say 4 is the number of adders. Also, there is one more thing for the time steps 2, if this guy can be scheduled over here and this guy can also come over here, there can also be a possibility. So, and there is only one multiplier in that case. So, you have to also write O62 is less than equal to 1 max. So, what do I essentially say that for time step 2 what is the possibilities? For time steps 2 you can see, that this divider can be scheduled, possibility, it may also go down but possibility is there. So, you have to write O32 plus O72 is less than equal to number of dividers. Similarly, this multiplier can also come down, there is a possibility. So, you write that O62 is less than equal to 1 max because there is no more other divider. Similarly, 9 can be scheduled over here. So, we say that O92 is less than equal to number of this adder maximum. Similarly, this subtractor can also come over here. So, you write that O82 is also less than equal to say 3 max. So, this is how we are actually writing the resource constraint based equation. So, let us again go back and see in a more formal way what we are saying. Okay. So, in the first time step we are saying that O11, O21 and O61 represent that 3 multiplication operation can be scheduled 1, however, it should be less than equal to 1 max. So, this one is actually multiplied in step 1. Also, we saw that there was one subtractor in step 1. So, you have to write this. These are all about step 2. So, in step 2 we see that C6, that is operation 6 can also come in step 2. So, we are writing that O62 is less than equal to 1 max because there can be only one multiplier possible in step 2, that is 6, but there can be 2 dividers in step 2, that is 3 and 7. So, if 6 is scheduled in step 1, there is a possibility that 7 will be scheduled in step 2. So, we write that O32 plus O72 is equal to less than max and there was only one subtractor possible, that is 8. So, we write that O82 is less than equal to 3 and there was only one adder, that is 9, that could also be possible to schedule in steps 2. So, we write is actually O92 is less than equal to this thing, less than equal to the number of adders. Similarly, you can write this for step 3 and similarly you can find out that how to write about in step 4. So, I mean if you look at it, just one more example we will see for the time step 4. In time step 4 you can see that what are the possibilities of schedule, only this guy can be scheduled, that is O54, that is the subtractor less than equal to number of subtractor max, and this adder can be also scheduled over here, that is O9. So, O94 it should be less than equal to total number of adders. So, if you look at time step 4, so O54 is less than equal to number of subtractors and O94 is should be less than equal to the number of adders. So, in this way you can always you can find out for all these steps. So, till now what we have done, we have written this set of equations which represent the ranges, and these are the 6 of equations which actually says that your resources should not overshoot the total number of resources. But I have told you that again this number will be automatically minimized as much as possible by the ILP. So, now for the time you can think that now they are very high in number. Okay. Now, a very important thing is the data dependency. As I already told you, even if I do not say anything, data dependency is mandatory. Like you can see that O1, O2 are fixed in control step 1 and O2 is O3 is whose positions are fixed, like O1 and O2 are fixed in time step 1 and O3 is fixed in time step 2. So, like how do you say that? So, we say that if you look at it, so what do you say? We say that O1 is equal to 1, that means it is fixed at 1, O2 1 is 1, that means it is fixed at 1, O3 2 is actually fixed at 2. That means what? O1, O2, the output will be joining and you are getting as O3. So, this is all actually fixed at O3, then O4 will be scheduled in 1, that is actually O4 is scheduled in time step 1, 2, 3, and similarly O5 is actually scheduled in time step 4. So, these guys are time dependencies are already fixed. So, I mean O3 is dependent on O1 and O2. So, this 3 stuff satisfies that. Similarly, O4 is dependent on O3. So, O32 is scheduled in 3 is scheduled in 2 and then 4 is scheduled in 3. So, by just with these two equations this dependency is satisfied, and by this one and this one. So, you know that 4 controls 5. So, 4 is scheduled in 4 is scheduled in time step 3 and 5 is scheduled in time step 4. So, these two equations basically controls this dependency. That means, these 5 equations control the dependency, automatically take care of the dependency of this graph on this subpart. But there is a problem, like we will see. So, that means in this case, so O1, O2, O3 and all actually are scheduled after O2. So, O1, O2 and O3 has been taken care of by the equation. So, not only O1, O2, O3, O1, O2, O3, O4 and O5. So, all these things are actually taken care of by this first 5 equations. So, these first 5 equations if you take, they take care of this first 5 equations if you take, they take care of this dependency, that this dependency has already been taken care. So, this is a dependency that has already been taken care in this case. Okay. Now, we will see about this. So, there is a big problem over here. So, we will find out what is the problem. Now, you see, so this is one equation O61 plus O62 equal to 1. Okay, that is says that 6 can be scheduled in 1 or 6 can be scheduled in 2, but and also it says that 7 can be scheduled in 2 and 7 can also be scheduled in 3. So, there are 2 equations we have written, but there is a big problem over here. So, it says that 6 can be scheduled in 1 and 6 can be scheduled in 2, and this equation says that 7 can be scheduled in 1 and 7 can be scheduled in 2, but there is a mislink over here. So, there should be a link says that if 6 is scheduled in 1, then only 7 can be scheduled in 2 or 7 can be scheduled in 3, but if 6 is scheduled in 2, then 7 cannot be scheduled in 2, it has to be scheduled in 3. That is not being told by this 2 equations which are defining your range of operations. That is a big problem over here. Similarly, you can also find out that this is also a big problem over here. So, these 2 equations if you think, it says that equation 8, operation 8 can be scheduled in 1, 2 or 3, and this one is saying that operation 9 can be scheduled in 2, 3 and 4. But if and only if 1 is scheduled in 1, then only 9 can be scheduled in 2, 3 and 4. But if 8 is scheduled in 2, then 9 cannot be scheduled in 2, it can be scheduled only in 3 and 4. Similarly, if 8 is scheduled in 3, then 9 can only be scheduled in 4. So, that is not being represented by this equation. So, we have to put some more equations which will actually satisfy this data dependency constraint. Okay. So, what is that equation? So, we will just see for this 6 and 7, then that can be automatically extrapolated. So, what we write now? We write 1 into 601 plus 2 into 602 minus 2 into 702 and 3 into 703 is less than equal to minus 1. So, this is one more equation we have added and we will show that it actually satisfies this data dependency mechanism. So, what we have done? So, this is nothing but your this step actually. So, this is 61, 62, 72 and 73. So, what we are doing? We are producting actually these are the 2 equations, that is 6 and 7 data dependency has to be satisfied. So, what we do? 6 can be scheduled in 1 and 2. So, we write 1 into 601, 2 into 602, 7 can be scheduled in 2 and 3. So, we write 2 into 702 and 3 into 703 and that should be equal to less than equal to minus 1. So, we will not tell you formally or we will not prove that this equation is, I mean theoretically we are not going to show that this equation will take care of the data dependency, but it can be very easily illustrated and very easily intuitively shown that it can be done. Okay. So, now you see these are the equations. So, what are all the possible solutions? Solutions are like 1 0, 0 1, and in this case also it is 1 0 0 1. That is what is the possibility. So, what are the possibilities? 6 can be scheduled in step 1, 7 can be scheduled in step 2, correct. 6 can be scheduled in step 1, 7 can be scheduled in step 3, 6 can be scheduled in step 2, 7 can be scheduled in step 2, 6 can be scheduled in step 2, 7 can be scheduled in step 3. So, I mean these are the 4 solutions which are going to satisfy this equations. Okay. And now you can see that only there is a problem in this. O6 is scheduled in step 2 and O schedule is 7 in O6 is scheduled in step 2 and O7 is scheduled step 2. This is actually not allowed. Other things are possible. 6 in 1, 7 in 2 fine, 6 is 1, 7 in 3 is fine, 6 in 2, 7 in 3 is fine. So, only one problem is with this 6 in 2 and 7 in step 3, that is not possible. So, how it can be avoided? So, now we have said that so in this case now we are looking at this. So, now we have written this equation, additional equation we have written that O61 into this one. No, so, now if you see that if we are writing that O61 is in step 2, that means what? Actually this is going to be a 1. So, O62 is equal to 1, and in this case this has also to be scheduled in step 2. So, this guy is to be 1. So, 1 and a 1. So, O62 is a 1 and O72 is also a 1 in this case. Okay, others are 0, this guy is 0 and this guy is 0. So, in this case 2 into 1 is a 2 and again 2 into 1 is a 2. So, 2 minus 2 is 0. So, 0 is less than equal to minus 1. So, this is not valid and the equation is false. So, in other words what I am saying that we are not going to discuss formally how it is actually helping you out, but only thing is that we are just saying the procedure, the details are out of the scope of this course, but intuitively you can think that will do your job. So, what we are doing? So, we are actually multiplying, we are so 6 can be scheduled, any operation which can be scheduled in step 1, 2, 3, 4, 5. So, we are writing it as O61 into 1, O62 into 3, and if there is more possibility we will write 3 into O63 dot 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 minus the other operation where there is a data dependence conflict can be possible. So, we are writing O72 into 2, O72 into 3 dot 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 if it is possible, and that is equal to minus 1. Now, you can find out that only one is a problem where there is a overlap. Okay, so, and to make this is a overlap, the answer is this one has to be 1 and this one has to be a 1. This has to be 0 and this has to be a 0. So, that is 0 1 and 0 1, 0 1 and 1 0, 0 1 and 1 0 is actually leading to the problem. But you fit it 0 1 and 1 0 in this equation which is written additionally, this will not satisfy 0 1 constraint, and so I mean this one will not be taken into picture. So, with this additional set of equations like this one, and for O8 it will be what? 8 can be scheduled in 1, 2 and 3. So, we write 1 into 1, 8 1, 2 into O8 2, 3 into O8 3 minus 9 can be scheduled in 2, 3 and 4. So, we write 2 into 9 2, 3 into 9 3 and 4 into 9 4, that should be less than equal to 1. So, if you write this additional equation, so what you will find that data dependency based constraints are also satisfied. That is in this case what can be the violation? The violation can be if 8 is scheduled in 2 and 9 is also scheduled in 2, then you are in a big problem. Okay, then this is 0, this is 0. So, this is the cut. So, it is 2 into 1 minus 2 into 1, again it is not less than equal to minus 1. So, it is violated. So, you can easily verify that. I mean this is, if you write an equation in this manner. So, this is how you, this is generalized how you should write this equation, that is the range, whole range you write and you product with the number or step number and you subtract with the other part, then you get and you write less than equal to minus 1. So, this equation will automatically check that there is no violation in data dependency. So, if you write all these equations, then all the constraints are taken care, range, data dependency, as well as you have to solve the, you have to constrain or you have to restrict the number of resources, which is 1 max, 2 max, 3 max and 4 max. So, that initially we assume that it is very high in number. So, that is done. Now, ILP if you run, automatically it will minimize 1 max plus 2 max plus 3 max plus 4 max. That is the minimum number of resources you require, that will be minimized. This is your, you have to minimize. Okay, so, now if you run ILP, so I am not going into details how you solve the ILP, this is a very well known undergraduate course. Now, you solve this, so you will find that this one is going to be your answer. That is, these were your fixed, okay, and you will find that O61, 62 is equal to 1, that is 6 is scheduled in 2, 7 will be scheduled in 3, 8 will be scheduled in 1, 9 will be scheduled in 2, you equal 2 multiplexer, 2 multipliers, 1 divider, 1 adder and 1 subtractor. So, automatically this value will come into picture. So, in this case we have seen that ILP is going to give a solution which is the best. So, this is the best. So, now you can also observe that force directed schedule has also given the same solution, list schedule has also given the same solution. So, you may ask why ILP? Actually, now we will see with an example that ILP is always going to give you the best solution. all cases ILP is going to give you the best solution, but the time taken to solve this problem, and that is to solve these were not known, and how to solve so that all the equations are satisfied actually is a 0-1 linear programming problem, which is known to be NP complete. It is going to take an exponential number of time in the number of these variables. So, we are saying that it is exponential number of steps, exponential in number of operations. Basically, formally speaking, it is exponential in the number of these variables O1, O2 dot all the variables we have taken, it is exponential in that number. So, it is going to be a huge, you know, because it is the variables are dependent on the number of operations as well as the number of steps. So, it will take a very long time to solve, but it will give you the best solution. So, in this example, it was by chance that force directed scheduling and list scheduling has given the same answer, but in the example we will see in the question answer session that is not the case. There are some examples where FDS is not going to give you the best solution, but ILP is guaranteed to give you the best possible solution, because it takes care of all possible permutation combinations and then it generates the results. So, how it is done, you can think or you can read up some extra material which actually says that this ILP actually takes care of all possible permutation and combinations. It tries internally, I mean internally the equations are written in such a way so that all possible permutation and combinations are tried, and then it actually finds out the best possible solution, but actually time taken is so high. That is why we are actually bound to go to heuristics. Okay. So, that is what I was saying, that FDS same schedule is given the ILP, then why ILP, why not FDS or some other heuristic. So, that will be FDS, I mean so in this question answer session we will find out a case where FDS is not giving you the most optimal solution, but ILP is always going to give you the best possible this thing. Okay. So, before we go to the question answer session, there are some small issues that we have kept this lecture very simple due to various reasons. The first reason is we have assumed that all the operators are same cost in terms of hardware. Yes, we are assuming that adder is taking same hardware, multiplier is actually same cost in hardware, divider is same cost in hardware. So, we are thinking that we have to minimize adder, minimize multiplier, minimize subtractor, all things we have to minimize at equal priority, but the answer is no. Actually, multipliers and dividers are very high in hardware cost. So, and adders and subtractors are less in number. So, our schedule algorithm is not very simple scheduling problem as well as scheduling solution, because we give priorities that if you can reduce the multipliers or adders, multiplier or dividers or high cost hardware, then please go on do that, and in that process if you keep on increasing the adders and the adders and the subtractors and say comparators or hardware which are not very expensive number, we allow to do that. That is, we want overall hardware requirement rather than overall total hardware requirement rather than equal treatment. Like in this case we have thought that we want to reduce adder, multiplier, subtractor, divider all equal priority, but that is in reality not the case. If we try to reduce important ones like multipliers, divider, factorial computers, which are actually take more area in their implementation and more complex. So, we try to reduce those numbers, even if in that process the number of adders, subtractors or some simple hardware increases. So, that is not considered in this lecture. So, you can understand that will make our problem as well algorithm more complex. Then we take that, we assume that all the operations are done in one step, but that is also not true. Multipliers may be requiring 2 steps to do the multiplication, but adders and subtractors may do it in 1 step. So, you may have multiple step or variable size step or multiple time step based optimization for the scheduling. So, that will again make the problem very complex to solve. Thirdly, so we assume that all the operation can do one function only, but that is also not true. Adder can do addition as well, it can do subtraction. You know that 2's complement addition and subtraction hardware are very much similar. Similarly, multiplier and subtractor hardware also looks very much similar. So, one operator can do multiple operations. So, you know that. So, if I require in one time step 2 multipliers and 1 divider, and in the next time step say all dividers. So, basically you can reuse the multipliers for divisions and vice versa. So, actually all this, and there are many more steps, so which are not, we are not bringing into picture, but you can feel that if I bring all these important paradigms into pictures or important factors into picture, the scheduling problem becomes a very complex problem. We will be taking into care the multiple functionality, multiple time steps, then cost of each hardware may be different. So, if I bring in all these issues into picture, so really scheduling is a very difficult problem, and complex algorithms like I01, ILP or future exact algorithms are almost impossible to be applied. So, we keep on applying new heuristics so that you get a good solution, near optimal solution, but it may not be the best optimal one. Okay. So, that is that about it. So, let us come to the question answer session, which we were waiting for a long time. As well, meantime we were saying that we will give you an example where force directed scheduling will not provide you the best result. Okay. In the examples we discussed in the lecture, FDS was giving the best result, it was very equivalent to ILP, it was very much equivalent to what you call your list schedule, but generally speaking it is an example where FDS is not going to give you the best result. And in fact, you can find out that 99.9% cases FDS will give you a near optimal solution, but the solution will not be the optimal one. But it will be very near optimal, or in many cases it may be optimal. So, it may be, but in 01 IP it is guaranteed to be this one, but because the time complexity is the problem. So, let us take that this is your output and this is your out 1 and out 2. So, this is your schedule like A plus B plus C star D. So, A plus B plus C star D is there, the out 2 is E plus F star B. So, we add it and then start it. So, these are the steps. So, now we will go for FDS. So, first what we do? So, this is your this is actually as soon as possible. So, everything we move up. Okay, and this is your as late as possible, everything we move down. So, we can find out these guys are fixed. So, these guys positions are fixed, their range is fixed, and these guys can move over these 2 time steps. So, this is actually represented over here. So, the range of these guys is similar, 1 is 1 1, 2 is actually you can say 2 2, 3 is 3 3, and this one can move between 1 2 and this can be moving 2 3. Now, we have to optimize using this one. So, you can easily think that what will be the best possible optimization. So, I mean and also this thing will bring into picture that multiplier is a much higher end cost stuff compared to an adder. That also is a very well known thing and everybody knows it. So, that factor also being into picture. So, what is the best possible stuff? So, I will put this my adder over here and I will put my multiplier over here. Okay, then that is actually this schedule. Okay, so this will be between 2 adders and 1 multiplier. Okay, then we know that multiplier cost is much less. But if we take this case where we actually go for this schedule, in which case we actually say we schedule this adder over here, because you know that this adder we are scheduling over here, because we know that this adder can be scheduled between 2 and 3, then this will actually restrict this multiplier and this multiplier will be scheduled over here. So, now we will require 2 multipliers and 2 adders. Okay, so, that is actually a big problem. So, you require 2 multipliers and 2 adders. So, each cost becomes very high. Now, adder cost is also increased, multiplier cost is also increased. Okay. So, that may lead to a problem. So, we will now show that FDS can actually lead to this solution. So, now the thing is that, if FDS says that you have to take one operation at a time and find out the probabilities and then you have to schedule it. Okay, so, now in this case let us assume that we take adder first. Nowhere it is mentioned that you have to take multiplier first or adder first or which hardware you have to take first, it does not say anything about it. It says that you take any operator and try doing with it. So, let us take the adder. So, the probability will be 1 plus 0.5 because this probability is half. So, it will be actually equal to 1.5. Here also it is 1 plus 0.5. So, it will be equal to 1.1 plus 0.5. So, it will be equal to 1.5 for the adder. Here we do not have any adder. So, the probability is 0. So, now so you think that if I schedule the adder over here, so its probability will become 2, and if I schedule the adder over here, its probability will become 2. So, now nobody says that where I have to schedule. So, both of the case the probability will become 2. So, let us just take some time and let us think that I schedule it over here. Nobody says that you look ahead for the multiplier, you look ahead for some other operators or take other things in constraint. Pure FDS does not say that. It says that if both of them are equivalent, you take arbitrarily, but if something is 3 and something is 2, then go for the lower one. So, in this case nobody says that you look ahead for the multiplier or what constraints you are applying if you schedule the adder here, that nobody says. Okay, so, in FDS, so we schedule the adder over here. Now, what happens? Now, the multiplier by default you have to schedule it over here because the range is actually now 3 3. So, you require 2 multipliers and 2 adders, which is not the optimal one. So, if that is what I told you, that FDS can lead to a problem, because in this case we considered the adder first and we did not have any look ahead, that if I put the adder over here, then what is going to be my problem. But if you take multiplier first, then obviously your multiplier will be scheduled over here, it will not be scheduled over here, and then your adder will be scheduled over here. So, if you take multiplier first, but pure FDS does not say that. So, then you can think that I can improve on my FDS by saying that I will take the operators first which are high in cost, and then I will start with multiplier, then I will start with adder. So, you can say that even if I start with arbitrary sequence, but then I have to keep a look ahead, that if I put a adder here, then multiplier will be restricted, then what will be the case and all. So, all these things are FDS plus other heuristics, and that is how research goes on. But if more amount of intelligence you put in, more amount of complexity you will be putting in, and more towards ILP will be going in. If you put a very complex algorithm, that is actually nothing but ILP. So, we have shown an example, so that this was the best solution actually. you put a multiplier first and then you put the adder if you start with a multiplier. That is one is the FDS plus, where you are actually having an emphasis on starting with the operators which are high in cost like multiplier and divider, and then start with this one. So, in a nutshell what we have found out that, so FDS or A as soon as possible, as late as possible may not give optimal solution in many of the examples, but we can keep on modifying our algorithms like look ahead or giving some priority and all, so that we get good or near optimal solution or optimal solution in many of the cases, but the time taken is much less compared to what you call your what do I say about your 0 1 ILP, which takes exponential amount of time in the number of variables. So, life is like that. For most of the VLSI algorithms or problems we will see in this course are all NP complete, NP hard, which cannot not have a well known polynomial time algorithm. So, you have to develop heuristics and you have to modify the heuristics, like in this case we modified FDS plus priority with the amount of cost of the hardware and so forth. So, you keep on modifying your heuristics and you keep on getting better and better algorithms which will give a near optimal solution. So, in the next class actually what we will be looking at some kind of automated algorithms like automated algorithms, procedures for the binding, allocation and binding problems. So, scheduling is already done by the algorithms. Now, once the schedule is done, we will see how we can go about this binding, what you say about this allocation and binding problem. Thank you.